we learned that there exists a set K of four matrices, A1, came out, with no R1 connections, for which this condition that the integral of the distance to the p for whatever p you want of some sequence tending towards this set to 0 does not when we have that the sequence converges weakly to some limit. And our initial counterexample, or the initial thing the initial example we first looked at as an example for which weak convergence doesn't improve to strong convergence was just the standard laminate, right? Where we just took matrices A and B, which did have a rank 1 connection, and layered in layers like this. This is an example we've done many times. This is a key example. And showed that if we can make this construction, then for sure weak convergence of gradients doesn't improve to strong. The point about this is that now we have this is true for a set without rank 1 connections, where a priori we can't begin this construction, but this rather clever kind of pushing things off to the edges of this shape allowed us to actually show this. So it wasn't necessary to have rank 1 connections to kill compactness, right? Now, this example is also the example we use to show that if we have a differential inclusion into a set with a rank 1 connection, then there isn't any regularity of the gradient, right? So that's where we were. So the laminate which is what this is, also showed us that if, let's call it O this time, I'm doing this in 2 by 2, but it can be any space, has a R1 connection, then no regularity. Of the differential inclusion du belongs to O almost everywhere, right? And the examples where we did see differential inclusions improving regularity were things like the conformal matrices or the rotations, which didn't have rank 1 connections, right? So given that we now know that it's not necessary to have a rank 1 connection to kill compactness, the natural question is, do we need to have a rank 1 connection to kill improvements of regularity of the differential inclusion, right? That's the thing we're now going to consider. So, question. Do we need an R1 connection for regularity to be false? Or I should say improved. On more generally, do we need a rank 1 connection to even build a non-trivial example of a differential inclusion into a set? Because that's the basic construction we've been doing all the time, is just to take a rank 1 connection and build something like this, right? So you might think perhaps this is true because, or perhaps it is possible to do this without a rank 1 connection, because what did we do with this construction to counterexample compactness? We found a sequence of sets whose gradients more and more lived on these 4 matrices, right? So we found a sequence of functions whose gradient was up to epsilon inside these 4 matrices, and outside of that, on a set of whatever epsilon, then it took some other gradients, right? Which is almost a differential inclusion, but not actually a differential inclusion. Yeah. So another way to ask this is that could we just push it a bit further and say, is that can we force the gradient to live on a set without any rank 1 connections? Yeah, like this. Well, in particular, to live on a set without any rank 1 connections that is also finite. So we do have that there exist non-trivial examples of functions whose gradients live on sets without rank 1 connections, but could we do it something like this, where we just have a finite collection of matrices? And that's one of the questions we're going to be studying. So why is that question interesting? So let me write that down. So that's question 1. Do we need R1 connection, an R1 connection for improved regularity to be false? Question 1. Question 2. Can we construct functions whose gradient lives on a finite construct, non-trivial lives on a finite set without connections? So it's a fairly related question. So why? Go ahead. Oh, I see what you're saying. Yeah, can we construct non-trivial, I should say, Lipschitz functions? Yeah. So if we were admitting completely discontinuous functions, then yeah, it wouldn't be difficult. Yeah. So why are these questions interesting? Well, there's a couple of reasons. First reason for me is that this question 2 is an elementary question that anybody can understand. Anybody with studied multivariable calculus can understand. So if I give you a finite set and it has a rank 1 connection, then you can trivially do it. If I give you a finite set without one, then you're probably going to be quite stuck, right? And if you thought long enough, you might say, okay, well, I can do it up to a set of 0 measure if you come up with a Tata square. But to actually, get something which exists almost everywhere inside this finite set of matrices and be a non-trivial function, that seems to be a very hard thing to do, given the methods we have, given what we know how to do. Yeah, for me, I am particularly attracted to elementary statements and theorems and questions, and the question 2 is exactly in that category. Go ahead. Yeah, or yeah. But well, either way would be good. So if you could find any finite set for which, if you could find any non-trivial Lipschitz function whose gradient lives on a finite set without rank 1 connections, that was also, that's also, I mean, it's a weaker statement, but that's also quite a strong thing to be able to do, given the only method I've shown you to construct differential inclusions is just to build things out of laminates. And the first question is interesting because of, I mean, these are closely related questions. The first question is interesting because there is a way to turn PDEs into differential inclusions, and some very old questions in regularity of PDEs have been solved via getting a negative answer or getting a positive answer to question 1 via constructing non-trivial mappings into sets without rank 1 connections. So a bit of background. So questions from PDE. So in calculus of variations, we're minimizing typically an energy. So this would be a typical calculus of variations problem like this. So U is a vector valued mapping, and we would have an energy like this. Let's just take U to be something which is from a domain in R2 into R2. Okay, so if we minimize this kind of energy, then, I mean, this is stuff I'll go into later perhaps. If we find the minimizer and the minimizer exists, then it's going to satisfy something called the Euler-Lagrange equation. And the Euler-Lagrange equation is completely analogous to a critical point where you have a local max or local min of a one-dimensional function. And so if we have that U is a local minimizer of this energy like this, then what does that mean? That means that T goes to I of U plus T phi has a critical point or is locally minimized at T equals 0 for any test function like this. And in particular, just by taking the derivative of this expression, taking this derivative through, you're going to get a weak solution to the following system. Divergence of gradient of f of this is equal to 0 in the weak sense. So I'm going to write like this. And that means divergence of the first row is equal to 0, divergence of the second row. So f is a mapping from 2 by 2 into R, so its gradient is can be thought of as a vector in M 2 by 2, right? So we're going to take the divergence of the first row and the divergence of the second row. That's a system, and this is the Euler equation, Euler-Lagrange equation of this minimization problem. And it's not hard to see that, and I'll perhaps show that in a second, or not in a second, but shortly. But the question for PDE, no, it's divergence of the gradient of f. So I mean, if we just, okay, so maybe I just do the calculation now. So if we look at this expression here of I of U plus T of phi minus I of U over T, right? If it's locally minimized at 0, then this derivative will be 0. And then what are we going to have to do? We're going to have to pass this through this thing, the limit as T goes to 0 of f of du plus T of phi, T of d phi. minus f of d of u over t, and then it's just the chain rule will give us the following thing. So assuming we can differentiate through this and pass the limit and all that good stuff, then what are we going to get? We are going to get the gradient of f of du, and then dot product with, I should use the same notation, d of phi, like this, and then integrating by parts gives exactly this thing. So this is divergence like this. Yeah, because, I mean, we can write out this thing coordinate-wise. What is this? This is the sum I j equals 1 to 2 of f comma ij, like this, du of comma j, like this, yeah? And then integrating by parts, we will have that so let's just write it. So integrating by parts, we're going to have, this is minus the integral of omega sum ij equals 1 to 2, and then like this, right? So that's the divergence of the first row times this test function phi 1, phi 1, and then divergence of the second row, test function phi 2, phi 1 and phi 2 independent. So it means we have these two equations holding, we have a system of equations holding weakly in our region, right? So this is the Euler-Lagrange equation. To actually actually have a minimizer, you need some concept, some properties of your function f in one dimension, or if we are talking about mappings u from Rn into R, scalar valued mappings, then there is a very easy natural concept, and that's just convexity of f. And it's because convexity behaves well with respect to lower semi-continuity. In higher dimensions, it's more subtle. It's much more subtle, and the concept is something called f is quasi-convex, and this is the quasi-convex I mentioned before. If f is quasi-convex, then we can actually find a minimizer, and there's a famous theorem of Evans from the PDE book Evans, that if f is strongly quasi-convex and u is a minimizer, not a local minimizer, but no, it's actually, I'm not sure, right? Either a local or an actual minimizer. Yeah, I think local might be enough. But anyway, if it's one of those types of minimizers, then U has got partial regularity in the sense there is an open set for which the gradient is Lipschitz on that open set, and it's an open set of full measure. It's called partial regularity. If you simply have a weak solution of this equation, so it doesn't necessarily come from a local minimizer, you simply have this as an equation by itself. It was an open problem for many years, for decades actually, whether or not the equation by itself implied the same kind of regularity. And this was counterexampled using the fact that we can turn this thing into a differential inclusion. It's going to be a differential inclusion into a set without rank 1 connections, and it's possible to build a non-trivial mapping into that set. And this was the work of Muller and Sverek from around 2000, something like this. So being able to positively answer question 1 in the sense, or positive and negatively, being able to answer question 1 in the sense that we can show that it's not necessary to have rank 1 connections to prevent improved regularity. That allowed an answer to this old question from PDE, and spawned a huge amount of work. So since that time, people have, this is connected to names Sikahedi and Deleuze, used these methods and pushed them very much further to answer a whole host of questions about regularity of other systems of PDE, Euler equations, Navier-Stokes equations under various regimes. There's a very old conjecture called Onzaga's conjecture was ultimately solved using these techniques. So many annals papers in the last couple of decades have used the fact that it's possible to construct differential inclusions into sets without rank 1 connections to counterexample old questions in PDEs, and that's one of the hottest things in PDEs for the last couple of decades, I would say. And it's ongoing. There's a huge industry of people using these methods, as you guys know, the regularity of the Navier-Stokes equations is like a huge open problem, $1 million prize problem, and people are inching closer and closer to understanding the nonlinear PDEs of fluid mechanics using these kind of techniques. Okay, so that's why question 1 is interesting. Question 2 is also interesting for me because it's an elementary question about basic mathematical objects that wasn't known until fairly recently. And the answer does involve using techniques of quasi-regular mappings, which is why we're going to talk about it. So I'm going to raise the board, and then we're going to talk about the kind of background to answer question 2. To provide a partial answer to question 2. So it turns out the answer to question 2 is that if you have a set of gradients which has got at most 4 members, so 4, 3, or 2, or 1, then you cannot construct a non-trivial Lipschitz function whose gradient lives just on those finite sets. But if you have, but there does exist a set with 5 gradients that has no rank 1 connections for which we can construct a non-trivial Lipschitz mapping. So there's a complete understanding of the question too. And the negative part of that, showing that if you have 4 or less gradients without rank 1 connections, then you can only have affine mappings. That's what we're going to show using the theory of quasi-regular mappings. The positive answer that for 5 and above, that is what I'm not going to show. I could maybe give you a tiny flavor of those methods, but that's quite a lot more evolved question, and it goes a bit too far away from the general topic of quasi-regular mappings. But that's the direction we're taking this in. Okay, is everybody happy? Everybody clear? Okay, so we're going to begin with the following theorem. Suppose omega contained within R2 is connected and U from omega into R2 is K quasi-regular, then either U is equal to 0, and let me express it like this. Either determinant of the U of x is bigger than 0 for almost every x belonging to omega, or determinant of the U of x equals 0 for almost every x belonging to omega. So this is like a kind of a version of this theorem from complex analysis, that if you have a holomorphic function in a connected domain, then the zeros of this holomorphic function cannot have a cluster point inside, right? Because if they have a cluster point inside, you just take the Taylor expansion around that cluster point. Every single term of the Taylor expansion is 0. Yeah. So this is a little bit similar. If you have a quasi-regular mapping on a connected domain, then, or from R2 to R2, then either the set of points for which the determinant of the derivative is 0 has got 0 measure, or it's the entire thing. It can't be just partially, cannot have a set of positive measure for which the determinant derivative is 0, and then it's non-zero in other places. And since this is quasi-regular, the determinant controls the derivative completely, right? So if the determinant equal to 0, the derivative is actually completely equal to 0. Yeah? So, sketch proof. So, let B be the set of x belong to omega such that the determinant of the u of x is equal to 0. Okay. Suppose the measure of B is bigger than 0. Okay, so I have a couple of claims. First claim, well, okay, before I do this, let me set up the machinery. So we're going to use Stoilov decomposition. So as you can maybe guess, so by Stoilov, there exists a K quasi-conformal mapping G from omega into R2 and holomorphic phi from G of omega into R2. So when I say phi is holomorphic, I mean its identification as a mapping from the complex plane to the complex plane, such that we have that u of x is equal to phi of g of x, right? So this is the standard picture. Let's put it over here in this unused space. So if we have omega, then maybe u maps it onto something like this. This is u of omega. And then g maps it onto g of omega. And then phi goes down like this, right? And the g, again, we obtained by solving the Beltrami equation that defines the u. Yeah, that defines the fact that u is quasi-regular. So, cool. Since u is quasi-regular, it satisfies this Beltrami equation for some particular coefficient. And we just find the g that solves the same thing, but it's going to be quasi-conformal. It's going to be like the identity as we go out towards infinity, and but it satisfies the same Beltrami equation. And then we go back with g to the minus 1, and compose with u, and that gives us phi. Okay, that is how that stuff kind of worked. And then our first claim is that g to the minus 1, or the gradient of g to the minus 1, belongs to LP log for p bigger than equal to 2, for either p equals 2 or p bigger than 2. This is the first claim, and that's the claim I'm going to have to be sketchy with. The second claim is that if we consider the image of our bad set under G, then G of this image has to have positive measure. I'm just going to follow from the first claim. So if we have claim 2, then I'm going to show you how this follows. So suppose we have claim 2, then let's just apply the chain rule and take the derivative of this thing. So we have du of x is equal to d phi of g of x and the g of x. Let's apply determinant throughout. So we have determinant. Well, actually, let's do this all in one step. So we know that on the set B, the determinant is equal to 0. So if we take the integral over the set B of the determinant of u like this, then it has to be 0 because by definition this thing is 0 on B, right? But then by the chain rule, that's the same as the integral of B of determinant of the phi g of x, determinant of g of x, yeah, and then by the change of variables formula, that's the same as the integral of g of b of determinant d phi of w dw. Yeah? Everybody agree? Thumbs up if you agree. Hogo, the camera's focused on you as you're falling asleep. So while the camera is focusing on you, try to keep awake. Somebody could maybe do him a favor by speaking while he falls asleep, so I don't watch him collapse in front of me. So is everybody okay with this chain of equalities? Yeah? Okay, so if it was the case, if we had claim 2 that this thing was a set of positive measure, right? Then we have to have that the derivative of the gradient is going to be 0 on some set with actual cluster point inside, right? It's going to have a cluster point inside here for which the derivative is equal to 0, right? And then since this is also a connected set, because we have a continuous mapping homeomorphism between G and its image, this would mean that our mapping phi has to be identically equal to 0 on this entire set. Yeah? So since G of omega, well, since by claim 2, there must exist a cluster point of zeros of phi prime on you have this thing, and so phi prime is 0. But by the chain rule, we have that if phi prime is identical to 0 on this thing, then actually u is identically equal to 0 almost everywhere, because this is true almost everywhere. Yeah? Which implies that u equals 0 almost everywhere on omega. Yeah? So if we know that this thing has got positive measure, then we are done. Yeah? Cool. All right, so I claim that claim 2 follows from claim 1. So why so? So if we have claim 1, suppose that we have that the image of B has got 0 measure, then if we do this, let's integrate this set of zero measure, and let's integrate the determinant of the inverse mapping like this. Yeah. So by the fact that the determinant is controlled by the power 2 of the norm of the gradient, then this thing is less than to the 2, or if we have something bigger than 2, then we can take our subset B to be a bounded set, and therefore the image will be a bounded set under this G, and therefore we're going to have Holder's inequality. So this thing is the integral of an L2 integrable. This is an integrable function, the L2 gradient to the power 2, but we're integrating on a set of zero measure, so this thing has to be 0. Yeah. But then what is this thing? This thing, by, again, change of variables, this is just the same as the measure of B. Yeah. So that implies that the measure of B actually has got zero measure, which is a contradiction. We're assuming that it has positive measure. Yeah. So how does this work? So it's saying that if we have a set of positive measure that maps B onto a set of zero measure, then the inverse map has to expand things very dramatically. It has to take a set of zero measure and map it on a set of positive measure. And that's not going to be possible if the gradient is L2 integrable. Yeah? Or LP integrable for P bigger than or equal to 2. Okay, everybody happy? Okay, good. So claim 2 follows from claim 1. Yeah? So claim 1 is the part I have to be sketchier with. So we know for sure that G is an invertible mapping. Well, for sure in the sense that also was a sketch proof. Yeah? What we also know that G to the minus 1 is going to be a quasi-regular, or sorry, quasi-conformal mapping with the same dilatation, just by looking at the way that the matrix deforms the unit ball, right? So here's a little lemma. So if we let, okay, probably I'm running out of space. Let me erase the board, and then we'll talk about claim 1. So claim 1 again was that gradient of the inverse belongs to LP locally. Okay, so note, if we let, say, MK be the set of matrices in, I mean, this will work in n by m, but let's just do this in 2 by 2, such that the squared number is less than k times the determinant of m, like this, okay, then if A belongs to this set, this implies that A to the minus 1 also belongs to this set, like this, which is not too hard to see. So take A belonging to the set, and then A we can write using polar decomposition, we can write as a rotation, then a diagonal matrix consisting of the eigenvalues, which will be positive A1, A2, and then another rotation like this. We've done this before. First we do polar decomposition, we decompose into a rotation and a symmetric positive definite matrix, and the symmetric matrix can be diagonalized, so we end up with something like this. And the actual distortion of the unit ball is in terms of these A1, A2, right? So if we so assume without loss of generality that A2 is bigger than or equal to A1, then what do we know? We know that the operator norm is just going to be A2 squared, which is bounded above by k times A1, A2, and therefore that gives us this ratio that A2 over A1 is less than k, right? Yeah. If we take the inverse of this guy, of this matrix, then 2 to the minus 1, and then the inverse of the diagonal matrix. The inverse of the diagonal matrix would be a to the 1 minus 1, a2 to the minus 1, and then r0. I should have done not r0 and r2, but okay, whatever. Like this. Again, the distortion is depending on these eigenvalues, a to the minus 1, a2 to the minus 1. Start again, a1 to the minus 1, a2 to the minus 1. Since a2 is bigger, then a to the minus 1 is now bigger. So if we consider, so we've just seen that this thing, I mean, this is an equivalence right here, that all we need is that the biggest eigenvalue is controlled in terms of k, like this, or the ratio of the biggest divided by the smallest. But for the inverse mapping, the biggest is a1 to the minus 1 divided by a2 to the minus 1, right? And that thing is the same as a2 over a1. It's the same ratio, which is indeed bounded by k. So that implies that a to the minus 1 also belongs to mk, which isn't a surprise. Everybody happy with that? So if we have our mapping G, so if we have our G, which is quasi-conformal, so it's from omega into R2, and it's K quasi-conformal, then if the inverse was a sublaw function in any sense, then the gradient we can just calculate like this. It is dg g to the minus 1 of x to the minus 1, which will belong to this space like this too. Because the gradient certainly belongs to this space because it's k quasi-regular, right? So if we are in any kind of sublaw space, then such that we can create a gradient of the inverse mapping, then it's got the right form, and then the fact that it's a homeomorphism means that we'll have L2 integrability of the gradient because just because we have that the determinant controls the actual norm of the gradient, right? So so the integral of any region, say pi, of determinant of g to the minus 1 of x dx is just g to the minus 1 of pi, which is contained within omega. So it's something of finite measure, I should put like this. And that is less than the measure of omega. And then this thing, this is a positive quantity, and this thing controls above like this. So this is like 1 over k of the norm of the minus 1 of x squared. So if this thing has got any kind of sublaw gradient in any space, even L1, then it's in L2 just by the fact it's a homeomorphism, and then the argument follows. Right? So, but it is a slightly non-trivial thing to show that it does have a sublaw gradient. So this is if it does have a sublaw gradient, then we can do this. This is a step we can apply, but a priori we don't know it's differentiable, and but it is, and it's possible to see that. But the things I've told you don't allow me to give you an elementary proof. So that's something I'm just going to have to. That's the point I have to be a bit sketchy on. However, I hope it's not too hard to believe that the inverse mapping will also be a sublaw mapping, and therefore the integrability will follow easily, and therefore claim 1 is also not too hard to believe. Cool. So I'm probably over. Yeah. So the way I define quasi-regular mappings was in terms of they were defined as sublaw mappings because we have to have some notion of gradient just in the definition. There are definitions of quasi-conformal mappings that don't involve that, which involve this distortion of various classes of curves. And but I skipped all of that. I went straight to the so-called analytic definition of where you already have a derivative So yeah, it's not a trivial thing that the inverse is also quasi-regular, but that the inverse of a quasi-conformal mapping is also quasi-conformal, but it is, and that's what I have to ask you to believe. Okay, so over time, I'm just going to very quickly say how we're going to use this. So, theorem. Suppose there exists a set K of matrices A1, A2, A3, such that K has no R1 connections. Then, if the U belongs to K almost everywhere, so implicit in this it's a Lipschitz mapping, then the U is equal to AI almost everywhere for some I. In other words, if we are in this set, which has no rank 1 connections, there are 3 of them, then we're actually forced to be exactly one of them. Okay? And I claim this follows this is true, but this is not true when we have 5. This is false when we have 5. It is also true when we have 4, but it's a very surprising thing that it's false when it's 5. So we're going to use the previous result to prove this, and what would be a cool thing would be for you guys to try and come up with a proof yourself. So here's a hint. Consider W of Z, which is equal to U of Z minus, let's say, AK of Z for some choice of AK. i.e., we're going to have the W of X will therefore belong to 0. Let's say AQ minus AK, AP minus AK, where AP and AQ are what we have left after we take away AK from the set A1, A2, A3. Take away AK. Okay. So that's the hint. Try and think how we can prove this result using what we know above with this reformulation. But you have to choose the right AK, and then it falls out rather easily. All right, that'll be it for today. Any final questions before we sign off? Everybody good? Nothing about it. Perfect. All right, see you on Friday.